everybody drink?
Yeah. Is it good? All right, cool.
Okay. So this talk's going to be quick. It'll be sort of blitzkrieg. There's a lot of stuff in here and a lot of stuff that didn't make it in the slides. So if you got more questions, just let me know. I work for Connexus Consulting. I am an ex-government employee from NIST. I spent 20 years there, and a lot of this research came from there. So it's actually, a lot of the research and stuff like that is public domain. So there's actually some SourceForge stuff out there. About 85% of it is public domain, and the rest is proprietary. My company wants to sell this stuff. So, I work in the industrial space. So it's typically PLCs, programmable logic controllers, SCADA stuff, small industrial devices, things that are about this size, but they have to last for 20 years in a plant, and they've got an Ethernet TCP/IP stack. So it's stuff that is very simple, but it's stuff that has enough horsepower to do networking. And generally there's two sort of modes where most industrial devices live. There's one publish and subscribe, and one is command response. Not unheard of in the IT space, but they're very deterministic in the industrial space. So making sure that that communication is precise and comes exactly when they need it is very important. For publish and subscribe, the big thing you're dealing with here is you don't care about the time it takes when the communication first starts up. You care about making sure that that packet, you get a packet from that device every 50 milliseconds or every 10 milliseconds. Some of them are down at like 100 microseconds or lower. So you've got to get that device that may have an 8 or 16-bit microprocessor to send you a packet on a very regular interval. Measuring that's pretty important to make sure your system stays stable. You've got a control loop running inside those devices, and if you don't get data on regular frequencies, what happens is you can actually destabilize the control loop and actually send things into places that you don't want them to go. So, one of the protocols that I've done quite a bit of work with is Ethernet IP. That is Ethernet/industrial protocol. Very bad name, very poorly chosen name, but that's marketing speak. So in the protocol, it actually has what they call requested packet interval. That's sent down from a master device to a slave device, or to the publisher of the data. And then the publisher says, okay, I'm going to transmit at that frequency, sends back the accepted packet interval, but generally that's not what you actually get out of the device. So when we're measuring stuff, we use what's called measured packet interval, of course. Oh, it actually works. Cool. I didn't think that would actually work. So this is going into some time sequence diagrams here. So what you've got here is on the left you got the subscriber. So this is going to be a little bit bigger device actually doing the actual control loop, stuff like that. On the right hand side you've got the publisher. This is going to be maybe a remote eye device, which what those devices, maybe you got 24-volt signals or analog inputs and outputs. And what you're trying to do is actually get that communication from here to here. It's going over networks now. It used to go over serial lines or actual like digital or like straight up just wiring back and forth between those. Now it's all networked in plants. You don't care about what the initial time period to actually initiate the communication is, because you know that it may actually take some time for the protocol to go through. The publisher device actually has to set up the communication, set up the timer, set up the watchdogs, all that kind of stuff, and get things actually rolling. So a lot of the times that communication can take upwards of a second to get started, which in the IT world that's okay. In the industrial world, at 10 seconds they'll usually drop the connection and say, I didn't communicate with the device, and it starts the whole process over again. So they'll wait a little bit until it gets started, and then what happens is the publisher just starts throwing data out. It says, here's my data, here's my data, here's my data, here's my data. And every 20 milliseconds or 10 milliseconds or 5 milliseconds, it will say, it'll just send a packet out. On the subscriber side, a lot of times there's a heartbeat, or if it's actually a two-way connection, there will be data coming down from the subscriber to the publisher that's data that maybe you've got a motor or something like that and you have to change the speed of the motor, you actually have to send it the different voltages and stuff like that, because the control loop is actually being done on the subscriber side. So the intelligence is being done on the subscriber side, being sent down. So there's no guarantee that communication is going to happen in parallel. So the publisher may actually be sending stuff at 50 milliseconds, and the subscriber may be sending stuff at 75, 100, or something like that. But generally, it's going to be within a certain percentage, like 300 or 400%, just to make sure that you've still got something, so the publisher knows that it should still be sending data. So there's going to be some sort of heartbeat coming back from the system. So in this kind of case, the variability on that speed from the publisher is going to be really important to make sure that that's actually going to run in a relatively short amount of time, and you don't have, like, if you want 10 milliseconds, you don't have like 5 and then 15 and 5 and 15 or something to that effect. You actually want it to remain nice and consistent. So the other mode that you typically run in is command response. This is for a lot more of the protocols. A lot of the standard IT protocols run this way, client-server kind of stuff. And a lot of the other industrial protocols that may be older or they may be more specialized, they run a command response system as well. So in this kind of case, you want to make sure that the command that you sent back is responded to as quick as possible. You don't want it to sit there and the slave device to be sitting there and chewing away on that for a long period of time and then send you back a response with a lot of delay. So that latency is really important. So in this kind of case, what you've got is you need to actually make sure that that is within a certain amount of deterministic time. If it isn't, then that's going to send the whole system off as well. In this kind of case, again, you've got another timing diagram. The delay for the response delay on the responder side is what's really important here. Generally, the commander is going to be it's a higher power device. It's going to have more horsepower to it. It's not going to have the same sort of problems with communication frequencies and speeds. Okay, that's one device talking to another device. Generally, on industrial networks, you're going to get tens or hundreds of these devices talking to each other, and when we go in and do CVAs or designs and performance analysis on these networks that are running, it's not uncommon for these networks to be /23 or /22 flat networks. Yes, really ugly, and that's why they hire us to try and help them redesign it. But when you go in, you got to do an assessment first, and these are flat, ugly networks. So you may end up with hundreds, sometimes even like upwards of 1,000 devices communicating. And there's also no guarantee that one device is talking to another device and it's only talking one set of communications. On a regular basis, you'll end up with multiple communication streams coming from the same device to another device. And so you've got to try and overlay all this stuff and then do the analysis to actually figure out the performance of each one of these devices and each one of these communication streams individually, and you got to figure out a way to really strip those out and strip it down into just the important information for each one of those streams. To do that, you really got to know a lot about Wireshark. So it can be kind of hard to do, and like our software actually goes and does a CLI for T-Shark and writes this huge long string to try and pull everything out of that packet to actually do this. And it almost always requires post-processing. This isn't this kind of thing that you're going to sit in Wireshark and be able to do yourself. You've got to do this analysis outside. If you use Excel, you're going to do, I mean, we've got a software package that we use internally that we're trying to commercialize. It's not quite there yet. Okay, so yeah, multiple streams can exist between each devices. So we've tried to actually figure out what are the important pieces to pull out from sort of any different protocol. So we've actually developed, as part of this software we got an XML schema that allows someone to actually go and define for any protocol they want to define. As long as Wireshark can read it, this XML schema will allow you to define what the important parts of those protocols are that we have found for doing that performance analysis. So source address, destination address, source port, and destination port. Some of the protocols actually do things like they will use embedded timestamps in them. So they will actually use a hardware-coded timestamp that's maybe down to nanosecond level that's actually encoded at the end of the packet. instead of using the Wireshark timing that's actually captured, they've actually done a good job of hardware timing stamping. Some protocols use different addresses that are also encoded in there, so they're not using the IP address internally inside themselves. They're not actually using the IP address or the MAC address or whatever. They're actually using a separate hard encoded version of an address in there. So that you have to be able to pull out as well. And then for publish and subscribe, typically there's going to be some sort of connection ID associated with that. You basically have to say, okay, this is the publisher has to say that this is my communication stream that relates to this particular communication stream that you wanted. So here's my ID number when they do their initial handshaking, and then the subscriber just has to sit there and listen for that connection ID. And given that there may be multiple traffic streams coming from that same one device, you can actually now listen and find out and track individual traffic streams associated with that. So you can get some good layering over top of everything. And then there may be a sequence number to actually do some sequence, making sure you don't get out of sequence packets. Since TCP is not a guaranteed traffic stream, they made that assumption, and typically there's some sort of sequence number to make sure you're always sort of increasing. And if you get packets that maybe have dropped, or maybe they took longer, or they got retransmitted or something like that, you can throw them out because they weren't necessary, and you've already passed that, and you're getting data every 50 milliseconds anyway, so I don't care if I dropped one, I'm just going on the next one. So, and then for a command response type protocol, then you've got other ones. So there may be some sort of command message field that tells you, okay, when I receive a packet, this command means this type of actual, or this field means this type of command. Maybe it's a motor start command, maybe it's a motor stop command, or a change voltage or something to that effect. And then there's going to be some sort of response code associated with that. It may be the same actual portion of the packet. It may be a different portion. It may be just a different command number associated with that. But then you have to interpret the data along with that. And there may be a message ID. So sometimes with that command, you may not always get, you may be issuing 3 or 4 commands to the same device, and then you've got to wait for those commands to come back and see, unless you have some sort of identifier that tells you this command or this response relates to this command, you can't associate the two. And so there's usually some sort of message ID that's part of that as well. So here's the pretty pictures. This is actually a tool that we use when we actually go into plants and do things. What you've got here is, this is actually a 60-second test that we did, this is actually time on the x-axis versus delta time on the y-axis. So this is the measured packet interval here on the y-axis of this graph. And right down the center line, that's a 2 millisecond. That's 2 milliseconds right there. So we were supposed to be getting 500 hertz of data from this system. And you have everything from 1.2 milliseconds to 2.9 milliseconds. So the communication protocols assume that TCP is not going to deliver the messages. So they make the assumption that unless you get packets that are really late, they're not going to try and shut down the communications. They're just going to assume it's really late and something went wrong. Typically, though, what happens is when they're really late, it's not the network infrastructure that's the problem anymore. It's because the device that was sending it didn't have enough horsepower, or it had an operating system problem, or it had just some delay and it had a brain fart and it couldn't send stuff. So you get these weird patterns. And this herringbone pattern that you see here is actually something I've seen in multiple devices from multiple vendors. And it appears to be some sort of hardware-related clock skew that happens in devices. And I've never been able to do the root cause analysis to do that, but this is something that actually shows up in a lot of different devices. And then on the left-hand side, what you have is a histogram, which actually ends up being more of a frequency analysis because you've got 2 milliseconds and you've got a relative sort of frequency analysis for the strength of the signal at that particular frequency. So this is a publish and subscribe example. My next one is a master-slave example. And so it's really hard to see on this, but down at the bottom there are these big blobs of a bunch of packets very quickly with minimum delays in them. And then there's one really delayed packet at the top. And this is basically what happened here is you get in a lot of pictures of plants and stuff like that, you'll see these nice, pretty TVs with lots of different screens on them and stuff like that, and those are typically HMI screens, or human-machine interface screens. Those devices, when they go out and talk to the controllers, they talk and they will ask for a lot of different information all at once, and then they'll get a response, a bunch of information all at once, and then they have to wait until the next time slice when they're supposed to ask for that information. So what you'll end up with here is that you'll get minimum time delays on all that information coming down and all that information coming back, and then a delay. So what happens here is that this nice row of delayed packets at the top, the fact that that's a nice straight line across there is a good indicator that this is actually a well-performing system. And the reason this graph isn't nicer is that we're still working on some of it, and this is a generation, I'd say, 0.95 or something like that. So there's more work to do on this. But going into that a little bit more, into more of the math here, yeah, okay. I'm pretty much done. So there, so you got, this is sort of what happens. You get a bunch of packets all at once, and then time delay, quick succession, and if you know the company Rockwell, this is the Rockwell Automation. This is actually one of their protocols that they do, and this is one of the typical ways they do stuff. So where we're at right now, we're trying to commercialize our software to do this performance analysis. We need to streamline it. Right now, it's dev code, and we need someone that actually knows how to do Windows programming better than me to do it. So we're going to try and maybe hire somebody to actually do that. We are also trying to do a better command response kind of we want better graphs than this to show our clients. And so we want to actually be able to show some better stuff. So it's just trying to figure out the different way to do that. Build more math into it. We got to do more statistical analysis. Right now we're doing stuff that is just Gaussian, and we need to do a lot more with that. Add a lot more graphics, and then do some more protocols. And then here's my info. And I posted these slides up on SlideShare, and you can get them down from there, or ask me and I can send them to you.